All right, hello everyone. Welcome to end of week 5. Actually, a lot of you had midterms at this point. Are we surviving?
No.
No. Yeah, exactly. Awesome. All right, so this will be about x86 assembly. We'll be going over how to look at what your code compiles down to, because eventually, as we get into Rev 2 and eventually Pwn, you won't have the original source all the time. All you'll have is the compiled assembly. So we're going to teach you how to read it, write it, and call functions with it. To start, we have a meeting file on ctf@sigpwny.com. You can put in the meeting file for some points. It's the assembly category. I believe it's currently at the bottom of the meetings tab. So put that in. Yeah.
Okay, it's okay. We can come back to that later. So I'll be kind of kicking us off with just like an overview of what assembly is. So assembly is essentially just like a human readable abstraction over the machine code. So at the end of the day, we need basically the compiler needs to read binary. And unfortunately, we aren't too good at that. So we want basically a mnemonic to read what the CPU is basically interpreting. So from here, we can translate it to bytes, and then that's not always the most useful. So from there, we get our other instructions like add, and then also like our immediates. And we can kind of see here, like a simple C program kind of gets translated into a lot of assembly instructions. So under the hood, this is what your compiler is basically going to see. So when you run your like PDB or anything like that, it will see, you can probably see all these assembly instructions. And there's not like immediate one-to-one correlation. See here, the return will have a lot more assembly instructions with it, and we don't have like if statements on here, which will also have a lot more assembly instructions. But just as a whole, there's a lot of instructions for each line of C code. And we're going to be talking about like the 3 of the basic CPU structures here. So instruction memory, it's basically just your like a section of your compile code. It's what your program wants to be executing. And in x86, we have 16 registers for 64-bit architecture. Each of them are 64 bits wide or 8 bytes. These are more or less like quote unquote variables. They're not completely the same, but just for general purposes, we can refer to them as that. And then we have the stack, which manages our like function calls, local variables, all that fun stuff. And really briefly, we'll talk about instruction memory. It's just a contiguous memory of executable data. So most of our like sections of memory are going to be like read write or read only. And this is normally the only one with read and execute functions. So obviously we don't want anyone to be like writing to this because we don't want our program to be able to modify when it's executing, but we do want it to be able to execute. And also it is just at like a very low address space in general. It's below the stack and what we usually know as below the stack, the heap, even below that too. And we're going to have a special purpose instruction pointer register RIP, which kind of points to whatever we want to be executing at the moment. And we also have registers, again, for the x86 64-bit architecture. There's usually 15 of these. They're like, you see variables put in quotes because, you know, it's not kind of like your Python variables with like, or your Java variables like with types and stuff like that. But we can kind of think of it like that. So there's 14 of them that you can use for whatever you want mostly. Then we have 2 that you don't really want to mess with too much, which is the RBP, the base pointer, and RSP, which is a stack pointer. And we're going to talk a little bit more about this once we cover the stack. And another thing we want to know is that we can access like the lower bits of the register for naming. And you can kind of look at it here. So the 8 bytes is like our full register, but you can access just like 4 of those like lower bits, or 4 of the lower bytes with like the EAX for like RAX and so on and so forth. You can look at the table. Yeah, so if you do any manipulations with like just the lower bits, it won't affect like the bits that you're not working with at the moment. And now we can kind of talk about the stack. This is where all our like functions are managed, the local variables within these. So if we look at this kind of like stack diagram, it's actually usually flipped, but for the sake of just well, there's like 2 kind of reasons. One, because we're talking about like pushing and popping stack, and it kind of makes sense to look at it this way. And also, I think in GDB, when you're like, it also shows up this way. So yeah, it just operates like a normal stack data structure. You push to the stack when you want to add new data, pop to remove the top of the stack. Yeah, so kind of going back to what I was talking about with the registers on the stack. So there are these 2 registers, RVP and RSP, that are dedicated to like managing the stack. And the RSP will always point to the top of the stack. So if you want to allocate to the stack, you're going to just subtract from RSP, because remember, we're starting from like the top of memory. And then if you want to deallocate, you want to add to it. Now the RVP is, I guess, a little more complex. It kind of manages each stack frame of the function, but the value contained in each of these in the base pointer will be the RVP of the previous or the calling function, so that we can know where to go once we're finished, more or less. And then we can kind of visualize this here. So the RSP always points to the top. So if we have any more local variables, RSP is going to go upwards. RVP is underneath that, underneath the local variables. And then we have the return address underneath that, and any arguments that you passed into this function call. So we can kind of look at it in this really simple C function here. So this int a, it's at the very bottom, it's the argument. We have the return address, we have our save base pointer, and then also we have all of our local variables, and they're non-deterministically pushed to the stack. So it's not going to be exactly like the one-to-one correlation we have here. And also we have issues with like alignment. So if you have like a character that's only 1 byte, but I think mostly they want it to be 16-byte aligned. So that's also something to keep in mind. And so a quick note on syntax, there are, for x86, we have like the Intel and the AT&T syntax. So yeah, we'll kind of look at that here. I guess you don't really need to know like the exact like translations or anything like that. It's just good to note that there is a different like syntax for like AT&T or something like that. So just like a couple of different things, the Intel will have like the registers just without being prefixed by like the % sign. And then whereas AT&T will have that prefix for that, and then intermediates where it's prefixed by the $sign. And then the comments are different as well. It's just something good to keep in mind when you're interpreting these instructions. Okay, I'll pass it off to Sam.
The other thing to keep in mind about AT&T is that it switches the order of instructions. So the destination register ends up being the last argument in your instruction. Also, if you have mixed types, every instruction has to have a typing prefix suffix. So the reading AT&T assembly can be like extremely verbose and complicated.
So this is some example of just basic assembly. There are 2 columns of it.
We have a bunch of different commands. So the first item in an instruction is just a mnemonic. So most assembly instructions are about 3 to 4 letters. Granted, you get outside of the standard like integer working, they'll get very much longer. But for things like, you know, add is gonna add RAX and RBX and store it in RAX. Subtraction will take whatever's in DX, subtract it by OX1235 and store it in DX. This is an instruction you'll actually see a lot when you start looking at compiled code. This is much faster to zero out a register than it is to like move 0 into it. So you'll see compilers use that a lot as like a shortcut. You know, this is increment. No op is just do nothing. Technically, the special thing about no op is your processor doesn't actually have a like special case for no op. What this is an assembler alias. So your assembler is kind of like programming language itself. So there's some extra shortcuts it gives you to refer to other types of commands. So no op's actually an exchange command between RAX and RAX, which does nothing. And yeah, some instructions like integer multiplication can, or sorry, immediate multiplication can take 3 arguments. Some may take 4, some may take 9. The other thing to keep in mind about assembly is how we implement logic flow. So there's when we write if statements and while loops and whatnot, we need to be able to jump to other positions in the code because we can't just keep running instructions in order. So there is the simple instruction jump to address if we want to just jump to somewhere else. When we write these commands, how they show up in code is a relative. So this jump might be, hey, jump to -20. So if I'm at position 100 and it says jump -20, I go to position 80. I don't specify position 80 exactly. But you can have long jumps which require you to specify the address in full. And jumps are kind of the only way we can write to RIP directly and safely. x86 assembly also has conditional jumps, but it's basically all determined by subtracting 2 values. And we can get a lot of information from subtracting 2 values. If we get 0, then we know the 2 values are equal. If we get a positive number, we know that A is greater than B, and a negative means that A is less than B. So we have this instruction called compare, and it will just subtract the 2 registers you give it, and there's a special purpose register called rflags, which stores all of these bits of information on whether it was 0, positive, negative, overflowed, carried, so on and so forth. And so we have these conditional jumps. So the CC is just like a fill with condition suffix that is based off of whatever 5% FICO pair. And there's a table of 64 of these conditional jumps to select from. So this is a bit of code that we have to kind of show what logic flow would look like in an assembler. We set 2 variables to OX20 and OX15. We do this compare before we try to do a conditional jump. So we use the NE suffix to say not equal. So if these are not equal, we jump to bar. Bar will decrement RBX by 1, and then we'll jump back to foo like directly, and then we run this code again. And before we leave, we zero out RAX with our XOR command, and then we use ret to return back to our calling function. And that will pop things off of the stack to maintain that. So with the stack, there are some special purpose instructions to help you use the stack efficiently. You can just use push and then specify either a register or an immediate, and that will just push that value to the stack. And RSP will be automatically maintained for you. You don't have to mess with RSP directly. Pop does the same thing. It'll take whatever's at the top of the stack and put it into the register you provided. And again, RSP is automatically incremented. So this is how your stack, automatically maintains memory, and you don't have to clean it up because these instructions are messing with the structure of the stack directly. So this is a bit of a small like demonstration. So this is some code we're gonna run. This is the start of our function. Both our stack pointer and base pointer point to the saved base pointer. And this is the state of our two instructions. So right at the start, we move a new immediate into RAX. Move will zero out the rest of the register. It'll just assume that you want to replace the entire value with that. And then we can push that to the stack. And so now that push moves RSP up one and has added it to the stack. And then we can, again, zero out RAX, and then we can pop into RBX. So we've removed it from the stack and now we've moved it to RBX. And so that's generally, how assembly interacts with the stack. Finally, let's talk about syscalls. So we write functions in C to do everything we want, right? Whether it's to have a main function or some function to create objects, etc. But we do call special functions when we want to interact with the computer as a whole or the operating system. These are functions like read or exit or open or execve. Your standard library provides wrappers. Okay, that's fine. Your standard library provides wrappers around these syscalls, so you end up calling them from the standard library. But assembly does allow you to make these syscalls directly without ever needing to touch your standard library. So, to use a syscall, there's a few steps you need to do. One, you need to load the syscall ID into the first RAX register. The Linux source code gives you the list of syscalls to what function it will do. And that will be the most up-to-date resource, but I have better resources to actually reference later. And then you're going to load the arguments of that instruction in the following order. So the first argument gets stored into RDI, the second argument into RSI, then RDX, and then as we get into 64-bit compatibility, R10, R8, R9. And then finally, there's a special syscall instruction, and that will read the ID in RAX, call the function, pass the arguments, and then when the syscall returns, it will move it back. It will move the return value into RAX as the result. And as you go through with the debugger, you don't step into that read call. Once you call syscall, it just steps over it, because at that point you've given up control to your operating system, and you let the operating system handle it and then give control back to you. So this is a couple examples of setting up some syscalls. So if I want to exit with return code 10, I would move the exit ID into RIX and then move 10 into RDI and just call syscall, and that would kill my program. The other one, and this one is going to be more important as you reverse engineer and do Pwn. This will replace my program effectively and call a shell, which gives me access to the complete file system as if I just opened a terminal on the computer that's running this program. To just call execve with binsh, I can again move the execve ID into RMX. I have this assumption that I've placed the characters for binsh onto the stack. So RSP acts as a character pointer to that string. So I'm moving RSP into RDI. So now RDI holds a pointer to the string binsh. And then I want to zero out these other two arguments, otherwise I might get into undefined behavior or it tries to access them and crashes. And then I call syscall. And then what will happen is that my program will just become a shell, and I'm able to access files, run other programs, and so on. So as we talk about pointers, pointers can get very complicated. You might have already worked with them as you've done, 128 and 225. You might still just be going through and learning with them. x86 has pointers and dereferencing, but it's very similar to just how C does it, but it's kind of inlined. So if you want to dereference the memory, you just surround the
pointer value that's stored in a register with brackets. This is the same as saying like RBX is a pointer and I do star RBX and I get the value that's at that pointer. Just in assembly, it's with brackets. But assembly also allows you to specify a few indexing like arithmetic to that pointer, which includes an index register, a scale, and a displacement. So we ask ourselves, like, how do we efficiently iterate through an array of integers, right? Normally, integers are 4 bytes. So in memory, they each take 4 bytes. So if I want to address to a new integer, I need to skip forward 4 bytes in memory. So I can store like an index, like, get the 7th element, and 7 will be stored in RCX, and a scale. So if I'm indexing through arrays, then I can use the scale to skip 4 bytes every time I'm indexing through an array. This displacement is kind of odd to just tack on there, but the main purpose is if you are iterating through, say, an array of structs, and so the value in that struct might not be at an exact position. It might not be like 0 aligned, so you have a displacement to access a specific value within a struct that might be very packed. Writing to memory works the same way. You would just make your destination register have this dereference operator, and so it would increment the in this case, it would increment the top stack value of the stack by 1. So yeah, here are some resources. They are on the meeting flag challenge as well. This is the manual to x86. It's very verbose, but if you have a question about how an instruction works, this is the best resource to look at. It will tell you exactly what it does, what it expects as inputs, and what it will do. A tool I really like using is this online assembler. You can just write some assembly, hit x64 and hit assemble, and it'll put out a byte string that you can just throw into Python and just send over the wire if you need. If you want to look at how syscalls are called, this is a very nice page to look at the table of syscalls and their arguments and what needs to go into what register. If you want to do a bit more low-level work, you can get an assembler installed onto your device to assemble code into binaries. And then Compiler Explorer is very useful to see how C code turns into assembly. So you're able to write some C code. It'll show you the assembly that it makes and what blocks of assembly corresponds to what lines of C. So I have 5 challenges up. They're rated by difficulty. They each ask you to write a bit more and more shellcode. Read the C programs carefully for the first 3. They're a bit confusing, but basically I give you a very small space to write a bit of assembly. I'm just asking you to make the program do something very specific by writing that assembly. Use Pro Tools. We will talk about Pro Tools more, but if you got it from the setup meeting, you can get started by just connecting to the process or the remote process on the server for CTF, and then you can just send a byte string that is what your assembly shellcode is, and then get into interactive to see the flag. And then next Thursday, we have reverse engineering 2, which is where we will talk about reverse engineering x86 binaries and see, how to interpret assembly into bigger and greater functions and see what programs are doing under the hood. All right, that's all. Any questions? Cool. We'll be around to answer questions as you work on challenges.